This is part one of a two-part review for the labs for Lab Test 2. And we're going to start in part one with Lab 4, which has to do with AnalogIn. Now, AnalogIn has two public member functions. One of them is read, which is going to return a value from 0.0 to 1.0, which is a floating point number. But we can also use double to give us double precision floating point to increase the accuracy of this reading. Another public member function is read_u16 for unsigned 16-bit number. And as you may recall, an unsigned 16-bit number is unsigned short. And it will return a number from 0 to 65,535, or in hex 0x0 to 0xFFFF. Go down here and click on pot. We're going to get this generic picture of a potentiometer, which has three pins here. One is connected to ground, one is connected to VCC, and the wiper comes out and is going to then give us our value coming out of a voltage between the ground and VCC, and our VCC for our system is 3.3 volts. So on the wiper, we're going to get a value coming out here, going into the A to D, which is a value from 0 to 3.33 volts. Now, this is our actual pot here, and we can see that this is ground, VCC, and then we've got two data lines. Of these two data lines, we're only going to have the yellow one connecting, and we're going to plug this into A1 up here. Now, you'll notice up here, we have for each of these analog inputs, we've got ground, VCC, and A1, A0 here. We've got ground, VCC, A2, A1 here. And as long as the device only has one active data line, as this does, then it's going to be put in here, and it's only going to use the yellow wire, which is on A1. When we hook our temperature sensor in, as you've seen before, it's going to use A0. So A0, A1, because each one of these, a temperature sensor and the pot, only take data in on the yellow connector, and that's where it's connected up. Now, when we right mouse click and copy this into Kyle Studio Cloud, it's going to come in and it's called Lab 4A with errors. And you're going to find that there's a number of errors here. And it's going to ask you how many errors did you have to correct in order to compile this code. Well, let's take a look again at the code. And one of the things you're going to find is this has to do with function prototypes and function definition. All function prototypes have to be terminated with a semicolon, so that's one of our errors. And we also have another error here. And if we slide down to the bottom here, we can see our function definitions, and function definitions do not have semicolons. So altogether, to make this compile, there are actually 4 errors that have to be corrected. At this point, our program is running, and instead of using PuTTY, what we can do is actually use the serial monitor just by clicking here and going to 9600 baud, and we can see that we've got short and float sitting here, and as I turn my pot to the left, you can see these numbers are going to change all the way up to 65,400 and something, which is close to 65,535. And we're getting 99.9, and the reason for that is we're multiplying the voltage we've got here times 100, because it would usually go 0 to 0.999. And again, we have to understand the read U16 is going to give us a number here from 0 to 65,535, or if we were to format instead of %D, we said %X, it would give a number here between 00 and 0xFFF. Now in part 2, it says we're always going to hook the temperature sensor to A0 and the angle sensor or pot to A1, as we've just seen. And we always have to make sure that the grow up shield switch is set to 3.3 volts. And so that means this switch here has to be flipped ahead because it's 5 volts here and 3.3, so it has to be flipped ahead. And it also asks if we want to connect the temperature sensor to A0 on the grow up shield and use the variable temp data as a label for A0, what would you type? It has to be lowercase analog, capital IN. Then we can put temp data and we can put A0. And that's what we would put in to actually set it up. And we can put over here, sensor connected to A0 on header. At this point, we're going to copy this link and bring in another program. Please be aware that there's two ways to waste a half a second. We can say wait _ms 500, or we can say ThisThread : sleep for 500, and it will do the same thing. So this will work in Mbed OS 5, but it doesn't work in Mbed OS 6. This will work in Mbed OS 5 and Mbed OS 6. Now in this case, when you run it, and under Freedom K64, which is our serial monitor, you'll see something like this. Now the big difference between this and using it in PuTTY is these symbols here will show up as degree symbols. Other than that, everything will look pretty much the same. So there's no syntax errors. there are errors in how the code is actually running. So let's take a look and see if we can figure out how to fix the code that isn't a syntax error and make this program work properly. Now the first error that's really here is this AnalogIn input 1, and it even tells you over here it should be A0 because that is where our temperature sensor should be. Now notice it's got A2 here, so we're going to have to change that because there's nothing physically hooked to A2. We're going to change that to A0, and that's going to fix one of our problems there. Now further down here we've got voltage equals input.read. But we can see here that voltage is set up as a short, and read is going to return a float. So the other thing we have to put in here is underscore U16, because we're going to need to use shorts to actually do calculations, and here's the calculation here. This is our resistance here, but this is our temperature here, which is 1 over log R and so forth, which is going to generate this pattern that you've got here. And as we've seen before, this is a negative temperature coefficient thermistor, because as the temperature increases, the resistance here is going to drop. Now when it hits a magic number of 25 here, if we look up here, that's 100,000 ohms or 100K. And so that's sort of like a voltage divider, but this is the pattern that you're going to get, and this is how you read off temperatures here based on this formula. Now this formula is going to be based on having a unsigned short, and that's why you have to have it set up this way. Now when you run it this time, you're going to see temperatures that make sense, roughly 24 degrees. And again, if you were doing this with putty, you would actually have a degree symbol here and a degree symbol here if you have putty set to code page 437. And notice here as the temperature changes, the resistance is going to change. Right now the resistance is at 105 and we're down to 23.9. And if I put my finger on the temperature sensor, you'll notice that the temperature increases, and notice how the resistance drops, because what we have here is a negative temperature coefficient thermistor. And when this hits 25, we're going to see precisely 100K ohms on here, 25.4. Now one other thing that can go wrong is if you happen to have the switch set to 5 volts instead of this, you're going to see 45 degrees, which is not the temperature, unless you're in a place like the south of Iran or something. So just make sure that that switch is set to 3.3 on your Grove shield, or else you'll get incorrect readings. In part 4 of the lab here, you can write down temperature values and the resistance values and take 3 or 4 readings. And from this, you're going to see as the value of R decreases as the temperature increases, which means it's a negative temperature coefficient thermistor. In Lab 5, we have the Grove backlit LCD display, and we're also going to deal with interrupts. Now the class member functions here are clear, locate, set RGB, and print. Those are the 4 major ones. But the new version 5 also has cursor, no cursor, blink, no blink, and other ones as well, but these are the main ones that we're going to use. Now one of the things that you're going to run into is that if you want to do a print with the LCD, you cannot print data directly, because the print for the LCD is a lot like a put string in C. You can only print text. So we need to use the sprintf command. It's like sort of a print statement, as we'll see, to format what we want as data into an array of characters, and then use the print to put it on the screen. Now the public member functions, the 4 basic ones, set RGB, will set the color of the LCD to a red, green, and blue value, where these values will be anywhere from 00 to 0xFF for red, green, and blue. We have a clear function which basically clears all the text, a print again which only prints character arrays, and locate where we have a column, and the column goes 0 to 15 followed by a row for 0 to 1. One of the things you have to make sure is when you download Lab 5B that it has the Grove LCD RGB backlight underscore version 5. Otherwise it's not going to work with the version 5 LCD that we have. And also when you open this up, underneath here you should have Grove LCD RGB backlight.cpp and .h. Now we've run this as debug. So what I'm going to do is I'm going to go here and hide our watch variables. I'm going to hide our breakpoints for now, and I'm going to hide the registers. So we're really only interested in our local variables here. And if we do a step over here, we've got buffer, and if we open up buffer, because we've set everything to 0, notice everything isn't set to 0 yet because it hasn't really done it, but any kind of character array is going to be filled with garbage until it's initialized. Now this is supposed to initialize it, but if we step over again, we can see that it hasn't finished this, and now at this point it has initialized all these values to 0. Now it's going to say lcd.clear and so forth, and we won't be able to see that on here because I don't have a picture of our LCD, but I just wanted to show you as we go down through here. Let's take a look at our sprintf here. So I'm going to set a breakpoint here, and I'm just going to run to that breakpoint. And at this point I've got reading space voltage, which is exactly what I had up here, reading space voltage, and that's in our buffer, and it will actually print this on the screen using the print command. So it's done that up here. Now we're looking at data here. So if I step over this, sprintf, and there's our data value, 0.000 space 0.000, because that's where our pot is now. And because this is an array of characters, including a null at the end, that's exactly what's going to be showing up on our LCD if we step over one more time. And if I turn the pot, I'm going to turn the pot to the left here, and I'm going to run to that breakpoint again. Right at this point, let's step over this, and we're going to have our new data, which happens to be 0.725, 2.414, and that is what is showing up on my LCD when I step over one more time. Now our microcontroller has two different types of interrupts. One is InterruptIn, which is an asynchronous interrupt, which means that some voltage is going to come into the microcontroller, and it's either going to rise or fall, and based on that rise or fall, it's going to trigger a bit of code to be run. And this is the code that it's going to run here. Now this code looks pretty much like a function definition, but it's not, only because down here we declare it to be pb.fall. Now notice we've got InterruptIn pb, and pb is what we've defined this to be. That's why we have pb.fall or pb.rise, and we're basing that on rising and falling of SW3. So in this case, when we push down on SW3, it's going to execute this code. But the way it works is this, is once you have this thing set up right at the start of main and go into a loop here, after every instruction it says, has the push button fallen low? And if it has, it finishes that instruction, goes up, executes this code, and goes back right to where it left off automatically. So after every instruction is executed, it goes back and checks to see, did this interrupt line fall? And if it does, add 1 to counter. So this can happen anywhere in your code. And so as you go through this, let's just take a look at our code now. It says if counter equals 0. Well, if we look at our code here, counter was set to 0 to begin with. So if counter equals 0 and we never push our push button, it's always going to hit this if, turn off green and blue, and only turn on red. So red is going to stay on all the time here until you push your push button. Now when you push your push button and it changes counter to 1, it's no longer going to hit here. It's going to go down to this one where it's shutting off red and blue and turning on green. So every time you push it down, it's going to go to the next one. And then once you get to here and counter is now 3, you reset counter back to 0, shut off blue, and you go back here. Now there's another possibility here. You can also enable and disable the IRQ. Now by default, when you first set this up, it's going to be enabled, but you can also disable it, which is going to be part and parcel of what's going to be in our project when you deal with that, and we'll talk about that later. Now if we look at this code, it looks very similar. We've got void, count me in void with just adding 1 to counter and counter set to 0 as we've had before. But in this case, we're not using an asynchronous interrupt. We're using a synchronous interrupt, which is based on a clock. So ticker is what we use to say color change, and then we can say color change, not rise or fall this time, but color change dot attach. And then we're going to say ampersand count me in. Why is it ampersand? It's the address of this function. And then we're going to say every 2 seconds, it's going to then add 1 to counter. And counter starts off at 0. So in this case, as we go through here, it's changing counter every 2 seconds. So as you go through the counter, once you attach here, and you go through this stuff here, as you go through here, it's going to have counter 0 as we had before. 2 seconds later, it's going to change counter and add 1 to counter. 2 seconds later, it's going to change it to here. And then it's going to reset this back, and it's going to go back again and start the whole process again. Instead of you pushing the button to make it happen, it's going to happen every 2 seconds because it's a synchronous interrupt. Now, besides attach, you can also detach. So if in this case, if we have counter doing this stuff. If we hit our right push button, then it's going to shut off all the colors, wait 3 seconds, set counter to 4. It's going to do color underscore change detach, which means that every 2 seconds it's not going to do anything anymore. So attach sets it up to do it every 2 seconds, but you can always detach that to make sure it doesn't. Just like on the InterruptIn, you have enable and you have disable to shut off that type of thing happening with interrupts.